All right, hello everyone. Welcome. And today is the 147th video that we've done on the reciprocal system of theory. And this is a theory of everything that was devised by Dewey B. Larson back in the 20th century. And he died back in 1990. We're looking at one of his books from 1979 called Nothing But Motion. And we are in chapter 4 of that book called Radiation. So he's going to go kind of into the mechanics of the photon. This is a little bit controversial within the reciprocal system. Some of his followers have disagreed with his ideas about the photon, and we'll look into that a little bit later in future videos. But today we're going to let Larson air it out and explain what his conception of the photon is, and then in future videos we'll look at the critiques of that. Now, the basic idea of Larson's reciprocal system of theory is that we live in a universe of motion. Not a universe of matter and not a universe of energy, but a universe of motion. And for Larson, motion is the relationship between space and time. Space and time are therefore reciprocals of each other. So just the way that 3/2 and 2/3 are reciprocals of each other, they are inversions of one another. And so too in motion, you have either time and space as the numerator and the other one as the denominator. And then it can be vice versa, kind of depending on what scientific phenomena you're talking about. So if we have speed as we know is space over time. The car is moving 10 miles an hour, 10 miles of space in 1 hour of time. That is speed. That's the most basic kind of motion that we know of. But there are many other kinds of motion, and they are all relationships between space and time. We look at acceleration. Acceleration is space over time to the second power. You know, if I dropped a stone out of the tower, it would fall to the ground at 9.8 meters per second squared. That is acceleration, 9.8 meters of space in, 1 second per second, or 1 second squared. So acceleration is space over time to the second power. We've got all kinds of other relationships that are also space and time. Turns out energy is time over space. It took me 3 hours to move that thing 20 feet. To move that pile 20 feet. That is energy. That is time over space. Matter, in fact, is time to the third power over space to the third power. And that fits in with Einstein's equation equals mc squared. Energy, time over space, equals matter, time to the third power over space to the third power, times c squared, the speed of light squared. Speed is space over time. So space over time squared is s to the second power over t to the second power. You multiply it and it works out. E equals mc squared. So too, you can do that with any equation, legacy of the legacy science, to check, to see if the units work out. Once you kind of develop what those units are. We've got force is time over space to the second power. Capacitance is space to the third power over time. Pressure is time over space to the fourth power, and so on. So Also having to do with space and time. Space and time are reciprocals of each other. Therefore, they both have multiple dimensions, 3 or more dimensions, and they both come only in discrete units. There's no continuity. There's either you have 1 unit or you have no units. And then either you have 2 units or you just have 1. You don't go up by a fraction of the unit. You either have 1, you have 2, you have 3, you have 4, you have 5. But those units are so small that we see it as being continuous. So the unit of space is approximately 4.5 times 10 to the minus 8 meters. And the unit of time is incredibly minuscule at 1.5 times 10 to the minus 16 seconds, meaning that you get 6.576 quadrillion units of time per second. Okay, that's how small it is. A quadrillion is a 1,000 trillions, or it's a billion billions. No, it's a million billions. Okay, so those are the basic ideas behind the reciprocal system and where Larson's coming from. Right now, we're looking at chapter 4, and we're going to let him take over. He's talking about scalar motion and vectorial motion. Now, scalar motion is a motion, it's the basic motion of the universe. It's a motion without a direction, only a magnitude. And you can envision the scalar motion with a balloon and a magic marker. Take the magic marker, put a bunch of dots on the balloon, you blow up the balloon, all the dots are moving away from each other. But they're not moving in any particular direction. That's a scalar motion. It's a motion without a direction, or alternatively with all directions. You suck in the balloon, then all of the dots start moving toward each other, but in no particular direction. That is an inward scalar motion. So scalar has a direction, but that direction is only in or out, one of the two. Whereas a vectorial motion is, in a direction, south or west, or a combination thereof. Okay, let's let Larson speak here and hear him out. Ordinarily, the vectorial direction reverses in unison with the scalar direction. He's talking about the photon here. But each end of a unit is the reference point for the position of the next unit in the reference system. And conformity with the scalar reversals is therefore not mandatory. Consequently, in order to maintain continuity in the relation of the vectorial motion to the fixed reference system, the vectorial direction continues the regular reversals at the points where the scalar motion advances to a new unit of space or time. The relation between the scalar and vectorial directions is illustrated in the following tabulation, which represents 2 sections of a 1/3 or 1/3 simple harmonic motion. The vectorial directions are expressed in terms of the way the movement would appear from some point not on the line of motion. Okay, so he has here units number 1 through 6, and then he's got the direction in terms of scalar or vectorial. In the scalar motions, 1 is inward, 2 is outward, 3 is inward, and then 4 is inward also, 5 is outward, and 6 is inward. So what you have is you have 2 sets of 3, inward, outward, inward, inward, outward, inward. Whereas with the vectorial motions, you have an alteration of right to left, right to left, right to left. Okay, so the scalar motion is really accounting for the outward motion of the natural reference system. So the outward motion of the natural reference system is ubiquitous. It's always there. It's the reference system. So in Larson's system, the reference system is moving outward in a scalar manner. And so in order to have anything in the reciprocal system, you have to start out with an inward scalar motion, and then you can build from there. But you, because the inward scalar motion cancels out the ever-present progression, and then from there you can oscillate toward outward, inward, outward, inward. But you have to have the inward first. Whereas in vectorial direction, you're just alternating from right to left. Okay, back to Larson. The simple harmonic motion thus remains permanently in a fixed position in the dimension of motion, as seen in the context of a stationary reference system. That is, it is an oscillatory or vibratory motion. An alternative to this pattern of reversals will be discussed in Chapter 8. Like all other absolute locations, the absolute location occupied by a vibrating unit, the unit of simple harmonic motion, is carried outward by the progression of the natural reference system. And since the linear motion of the vibrating unit has no component in the dimensions perpendicular to the line of oscillation, the outward progression at unit speed takes place in one of these free dimensions. Inasmuch as this outward progression is continuous within the unit as well as from one unit of the reference frame to the next, the combination of the vibratory motion and a linear motion perpendicular to the line of vibration results in a path which has the form of a sine curve. Okay, now when you go over Larson's development of the photon, all I can really say is that it's very difficult to follow. You have to kind of read it over and over and over again, or listen to me reading it over and over and over again, and try to think abstractly, think with your, image-forming mind, and see if you can kind of picture what he's talking about. I don't think it's as difficult as it seems. It's more difficult because it goes against the way that we've been taught. So you have to unlearn stuff before you can kind of see it clearly. Okay, back to Larson. Because of the dimensional relationship between the oscillation and the linear progression, there is a corresponding relation between the vectorial directions of these two components of the total motion, as seen in the context of a stationary reference system. But this relation is fixed only between these two components. The position of the plane of vibration in the stationary spatial reference system of reference, the spatial system of reference, is determined by chance or by the characteristics of the originating object. Although the basic one-to-one space-time ratio is maintained in the simple harmonic motion, and the only change that takes place is from positive to negative and vice versa, the net effect from the standpoint of a fixed system of reference is to confine one component, either space or time, to a single unit, while the other component extends to n units. The motion can thus be measured in terms of the number of oscillations per unit of time, a frequency. Although it is apparent from the foregoing explanation that is actually a speed. The conventional measurement in terms of frequency is possible only because the magnitude of the space or time remains constant at unity. Okay, so there he's explaining how to calculate the frequency of the photon. What I didn't mention before, here he says, although the basic one-to-one space-time ratio is maintained in the simple harmonic motion, that basic one-to-one ratio, 1 unit of space in 1 unit of time, is the speed of light. Okay, so that's a basic relation that you have here. 1 unit of space in 1 unit of time is the speed of light. Here, in this oscillating unit, the first manifestation of independent motion, that is motion that is separate and distinct from the outward motion of the natural reference system, that has emerged from the theoretical development, is the first physical object. In the motion of this object, we also have the first instance of something moving. Up to this time, we have been considering only the basic motions, relations between space and time that do not involve movement of anything. Experience in presenting the theory to college audiences has indicated that many persons are unable to conceive of the existence of motion without something moving, and are inclined to argue that this is impossible. It should be realized, however, that we are definitely committed to this concept just as soon as we postulate a universe composed entirely of motion. In such a universe, things are combinations of motion, and motion is thus logically prior to things. Okay, so he's basically saying in order to accept the reciprocal system, in order to think on the level of the reciprocal system, you have to be able to think of motion being prior to something moving. Motion precedes something moving. The something that you see as moving is already motion. The something moving is the something is a motion. So you have a compound motion if you have something moving, because something already implies motion. And then when you move that, you have, a moving thing moving. Okay, like he says, in such a universe, things are combinations of motions, and motion is thus logically prior to things. Back to Larson. The concept of a universe of motion is generally conceded to be reasonable and rational. The long list of prominent and not so prominent scientists and philosophers who have essayed to explore the implications of such a concept is sufficient confirmation of this point. It follows that unless some definite and positive conflict with reason or experience is encountered, the necessary consequences of that concept must also be presumed to be reasonable and rational, even though some of them may conflict with long-standing beliefs of some kind. There is no mathematical obstacle to this unfamiliar type of motion. We have defined motion for purposes of a theory of a universe of motion by means of the relation expressed in the equation of motion. V equals s over t. Velocity equals space over time. Now just remember, velocity is a a vector form of speed. So velocity is the speed in a direction, whereas speed is just the space over time part of it. This equation does not require this equation v equals s over t. This equation does not require the existence of any moving object. Even where the object actually is motion of something, that something does not enter into any of the terms of the equation, the mathematical representation of the motion. The only purpose that it serves is to identify the particular motion under consideration. But the identification is also possible where there is nothing moving. If, for example, we say that the motion we are talking about is the motion of atom A, we are identifying a particular motion and distinguishing it from all other motions. But if we refer to the motion which constitutes atom A, we are identifying this motion or combination of motions on an equally definite basis, even though this is not a motion of anything. Okay, we're going to leave it right there. We may have to look at that paragraph again next time through, or at least the second half of it. But don't get discouraged if you are having trouble. Just kind of go through it slowly, and just, if you don't understand it, just kind of move on. Don't dismiss it because you don't get it. Just move on, suspend disbelief, move on to the next part. Okay, have a great day. Thanks for tuning in.